Today is recap the last lecture where we were talking about sources of parallelism, and we did 3 of the 4 different kinds that we have in order from most discrete to most continuous. We talked about discrete event systems, things like the game of life, where you have a finite number of different functions you need to evaluate, states of the machine. They all depend on some other finite list of information, like their nearest neighbors in a 2D grid, and then at every time step, for example, you may update them. The next more continuous thing that we talked about how to find parallelism and locality in was particle systems. So now I still have a discrete finite set of particles, but they're all moving around under F equals ma, say. And the interesting part is how to compute the forces on each one of them, which may be just an external force or just the nearest neighbors, or everybody could depend on everybody, and for which there are a lot of advanced mathematical algorithms that we'll talk about later to parallelize that. And then we talked about ordinary differential equations, which are even more general than particle methods, where again you have a discrete set of functions that can depend on one another, but they all depend continuously on time, say, and that could be a vibrating bridge or something like that. So are there any questions about those examples before we go on to the last, which is the most continuous of all, and talk about the other sources of locality and parallelism? So we had a whole list of different tools, and the one that hasn't come up yet until we get to partial differential equations is grids. So where you're sort of averaging with your nearest neighbors either in a structured way or an unstructured way. So what are the common problems that we had last time and that we'll have again? There's going to be load balancing, which could be either because there's not enough work to do or because the work is kind of irregular in how it's distributed. So we talked about how to do it statically, in which case if you have a nice 2D grid, that's pretty clear how to do it. But if it's dynamic, because all the particles collect in one place, then you may have to rebalance it from time to time. Locality has sort of the same issues. You can partition into large chunks with a low surface to volume ratio, and that's why small squares are a better way to divide up a big square than, let's say, long horizontal slices, which have bigger surface to volume ratios. And the whole goal there is to minimize communication, since that's the most expensive thing a computer does. And so if things are irregular, and we had a picture there where all the particles were collecting because they were attracting one another, then we're still going to divide it up into squares, but it's going to be done dynamically, and the dense regions will be divided into smaller squares than the large ones, and we had a quad tree as a data structure for that. And of course, as things move around, you have a tension between the two. You may start off with a nice load balance problem in a particle mesh method, but then if all the particles collect in one place, you may have to rebalance them. So now let's go see how all this, are there any questions about those examples from last time before we move on to some of the new features of PDEs? So there are 3 different kinds at a very high level of PDEs that are all going to have different issues with how they parallelize. And you don't have to be familiar with all the mathematics here. I'm just going to use these as examples because they do have different parallelization schemes. And at a high level, the 3 different kinds of equations are called elliptic. And those are things like, where everybody depends on everybody, so gravity, electrostatics. Hyperbolic, or wave equations, where all the information moves at a finite rate of speed and you only depend on your nearest neighbors. And then, what I'm going to use as a running example is parabolic equations, things like the heat equation, that combines both those features. And in that case, things are still time dependent. They change from time step to time step as they do in the wave equation. But now, at every time step, everybody depends on everybody else. So unlike a wave where information can only move at a finite speed, in the parabolic equations, when you write it down, everybody depends on everybody. Now, that sounds like it violates relativity, but don't worry about that. The physics is good enough for describing how heat flows and things like that. And so all of these have different kinds of dependencies that are going to influence how we parallelize them. So a global dependence is either going to mean we're going to do a lot of communication at every step, or in the parabolic case, we have to take super tiny time steps in order to get a decent answer. And locality can arise from either from finite wave speeds. That really means that information can't go too fast. And these are 3 very basic classes, and of course in the real world, if you have fluid flow, Navier-Stokes, or elasticity, you have combinations of all these different kinds of PDEs and parallelization schemes. So since I'm going to use the heat equation as a running example, let me start from scratch and just derive the 1D heat equation, which of course Fourier did a long time ago, but I just want to remind you of where it comes from. So I have an iron bar. One end is glowing red hot, and at the other end it's in some cold water, and it's blue. And what I want to do is write down an equation for the temperature at that bar, U, as a function of the position from left to right, x, which is going from 0 to 1, and the time t. And it's going to be a uniform material. So here is the intuition that Fourier used a long time ago. So suppose the temperature at these three different points, x, x minus h, and x plus h, are -1, 0, and 1. How is the temperature at x going to change? It's not going to change at all to first order because it's exactly on the average of its left and its right neighbors, so it shouldn't change. What if the temperatures at these 3 points are 1, 0, and 1? So in other words, the neighbors are hotter than the middle, the temperature should go up. And it should go up proportionally to how much colder it is than the neighbors. So all of that is entirely captured in this one line of equation. It says, how fast does the temperature change right there in the middle? So the time derivative with respect to x, well, what you do is you look at the difference in temperature there, how fast is it changing from x to x plus h? That is this difference. How fast is it changing from there to there? And you take the difference between left and the right. And that's going to tell you how much it's going to change. And so as h goes to 0, because this is all, I want to get a differential equation out of it, this turns into precisely the second derivative, and you get the heat equation. Okay, so that's our starting point. And what I'm going to do, of course, is go backwards and make this discrete, because I'm only going to be able to solve it at discrete time steps and discrete locations. So there's the starting point. And what I'm going to do, and when we did ODEs, I talked about two different ways of doing discretization, both whose name Euler was attached to. There was forward Euler and backward Euler. And they have trade-offs, so let me do forward Euler first. So what I'm going to do is replace all the derivatives in this equation by just divided differences. So there's how I approximate the time difference, t plus delta minus t divided by delta. And on this side, it's a second derivative, so I just go backwards to the same formula I had in the last slide. There's the derivative on the one side, the derivative on the other side. I subtract them and divide by h again. And so that's going to be my approximation. So now I've made it all discrete. And if I combine these terms, I get two copies of the temperature in the middle, which I subtract, and then I get the temperature on the left and the temperature on the right. So now, all I'm going to do to write down my algorithm is solve for the temperature at the next time step, because I want to go from time step to time step. And it's very simple, because the temperature at the new time step, t plus delta, only appears once, so I just solve for it. And here I have a formula which tells me everything I need to know. If I know the temperature at time t to my left and my right, I have a formula for the temperature at the new time step. So let me make this a little bit simpler, because this constant just appears in one place. So let me just call that constant here z. And so I get this nice, simple linear combination of my neighbors to my left, center, and right. And of course, I only want to evaluate this at discrete points. So instead of every x and every t, I'm just going to do it at positions x equals h, 2h, 3h, so I'll just j times h, and it only at certain time steps, time delta, 2 delta, 3 delta. And so I'm going to change my continuous function to an array indexed by time and space. And I finally get that the temperature at this particular, let me get this right, location and time plus 1 is a linear combination of 3 values of the temperature at the previous time step. So this is just a matrix vector multiply, right? I'm just taking linear combinations of a vector of temperatures at time step I and going to time step I plus 1. So let me just write down the code. All right, so before I write down the matrix, let me just write down the two nested loops which do all the work that I need to do. And so here's the formula I had on the previous slide. And I want to evaluate the temperature on this grid. So here at every grid point I'll have a value of the temperature. And the position is going to run from j equals 1 to n minus 1. And so the x-axis is the position. The vertical axis is time, so time is marching forward as I go up. And I also have to have some boundary conditions. I have to know, are the left and right ends of my bar in cold water or hot water? And then at every step, what does the inner loop do? It averages 3 numbers at the ends of the red arrows, combines them with the coefficient z, 1 minus 2z and z, and adds them up to get that one. So that is, what am I doing? I'm taking a vector of all these values, so it's the vector of this horizontal row of values of the temperature, and I'm doing a matrix vector multiply by a very special matrix called T, which is implicitly in this loop. And what I want to do is write down that matrix T, because I'm going to be using it a lot. And so there I've just copied down the formula to, I'm taking my average of my left myself and right neighbors. And so now let me vectorize. I'll use MATLAB notation. So here's all the different positions. I'll just make that a colon. And so I take the temperatures at time I, multiply by this matrix T, and get the temperatures at I+1. And there's the matrix T. And since I'm only doing left and right neighbors and myself, it's a tridiagonal matrix. And the coefficients are always the same. So you can, so the z's above, z's below, and 1 minus 2 z's. And to simplify this, I'm going to use the fact that z is a common factor for just about everything. So let me pull out the ones in the diagonal. That's the identity matrix. Everything that's left has a factor of z in it, or minus z. And so I'll pull everything out, and I'm left with this nice simple -1, 2, -1 matrix, which I'll call L, and L is the Laplacian. So, which is named after another famous mathematician. So I'm going to do a lot of work with this Laplacian. Here it's just a one-dimensional problem. It'll get higher dimensional in a few slides. And so at every time step, what I'm doing is multiplying by this tridiagonal matrix. And another way that people often draw what I'm doing here is with this, is to say, well, since I'm doing the same work at every mesh point, right, every row of this matrix is the same, then I'm going to express that by this stencil. So I'm going to draw this one-dimensional arrow, which indicates that I'm doing a one-dimensional problem. I'll have a dot at every mesh point where I'm discretizing it. And I'm just going to write down the coefficients once. I take 1 minus 2z times myself and average with z times my nearest neighbors. So this is a nice simple tridiagonal matrix in one dimension. For a two-dimensional mesh, so in that case, we'll see a picture of that later, I'm averaging not just with my left and right neighbors, I'll also have neighbors above me and below me, so I'll have not 3 numbers in each row, I'll have 5 numbers in each row. And in 3 dimensions, I'd have 7 numbers in each row. So we'll see those later. So where does the parallelism come from? Well, this is, at every step, what am I doing? I'm doing a sparse matrix vector multiplied by this incredibly simple tridiagonal matrix, which is so simple we don't need too much machinery, but let me just apply that machinery anyway. So what I'm going to do is I'm going to partition my space, my mesh points, into p chunks if I have p processors, and here they are. And so if I have 4 processors, I just want to divide them up so everybody has an equal amount of work to do. So in this case, everybody gets 3 mesh points, and I want to minimize the surface to volume ratio, and in one dimension that's pretty straightforward. There's only one edge connecting one partition to another, so there's only one word that needs to be communicated in each direction. And so, and as we talked about before, if I have a more general graph, there's algorithms for that. We'll have a lecture on it, but the 1D case is very simple. And this is kind of all you need to know for hyperbolic equations, because I'm only ever going to get my nearest neighbors, wave speeds will be finite, and average them and do a sparse matrix vector multiply at every step. Now, what goes wrong with the heat equation? Why do I have to think harder? So it turns out that if I just use this forward Euler approach that I just described, it's not numerically stable. I'll show you a picture of it blowing up in a second. So there's this number z that I had. What was z? It was the conductivity times the time step divided by the space distance squared. And this formula only works if the z factor is less than 1/2. I'll show you what happens when it gets bigger. So why is that a problem? So suppose I want to have finer resolution. I want to get the temperature at a closer together mesh point. So I make h 10 times smaller. That means I have to make the time step 100 times smaller. So this does not scale very well. But let me show you a picture. Let me try it anyway and see what happens. So here's a very simple simulation. So done 2 different ways. And so the vertical axis in these plots is the temperature. So up is hot, is red. From left to right is the length of the iron bar. So this is the bar that goes from one end to the other. And time is the axis coming out of the board. So here I choose Z just a little bit less than a half, so it should work. And I start with the ends in cold water, the middle is hot, and eventually it all cools off and it's all at the same temperature at the end. Here I just make Z a little bit bigger than a half, I think 0.58, and initially everything works fine, it starts cooling off, but then it starts blowing up exponentially, and that's just the nature of this particular mathematics. We have to do something else. It's going to be more challenging to parallelize. So let me go back and fix forward Euler just a little bit, and I'm going to use the same trick we did for ODEs. I'm going to, instead of using forward Euler, I'll use backward Euler. And so what am I going to do? I'm just going to use the same approximation, except instead of taking the space derivative at time t, I'll take it at time t plus delta, so at the other end of the time step. So this is almost the same as before, except I've changed t to t plus delta on the right-hand side. Now let me just take that and solve for all of the temperatures at time t plus delta, and I get all the t plus deltas over here, and there's the temperature at the last time step. So now I have a system of linear equations to solve. I have this linear combination of my unknowns equals something that I know. And so let me again write down the system of linear equations, and I'll use the same abbreviation I did before. Z is this combination of coefficients, and I'll just evaluate it at temperatures at times delta, 2 delta, 3 delta, at space resolution h, 2h, and 3h. And now it all turns into the right-hand side, which I know, at temperature at time I. Here's the unknowns at time I plus 1, and the coefficient matrix is very similar to what I had before. It's the identity plus Z times the Laplacian. And so it's the same Laplacian that I had before. So that's the system of equations that I need to solve at every time step. So everybody depends on everybody else, ignoring relativity, of course. And so this is a tridiagonal matrix. That's a super simple problem to solve. You can solve it in linear time. It gets much more interesting when we do it in higher dimensions. So for the, maybe if you're an expert, you'll say, okay, backward Euler isn't quite the right thing to do. What do people really do in practice? Well, they use something called the trapezoidal rule. But don't worry, we know everything we need to know to parallelize that too. I still have to solve a system of linear equations, except now instead of Z, I have Z over 2 in the coefficient. So I solve the same system of linear equations to a certain extent. And on this side, I just do another sparse matrix vector multiply, averaging with nearest neighbors. So, and that has a much better numerical properties, but it's still just a mixture of sparse matrix vector multiply and solving sparse equations. So we know everything we need to know. And so again, just to remind you, L is the Laplacian with 2's and minus 1's, and it's still that same stencil operation. So this is the heat equation. Now, I said that we also care about elliptic problems, and the famous, most canonical elliptic problem is still based on that Laplacian matrix. It's called Poisson's equation, and that's simply solving L times unknowns equals knowns in one dimension. So everything I'm telling you about the heat equation will also apply to elliptic problems like solving Poisson's. So are there any questions about this quick review of mathematics? Okay, so one more quick review of physics, and I'm done with that, and we'll go on to the parallelism. So why do we care about Poisson? What does it have to do with the gravity and the electrostatics that I told you about last time with particle methods? Well, if you remember your freshman physics, what's the force in a particle? It's an inverse square law. And so there's how I write down the force between a particle at the origin and a particle at x, y, z, where r is the distance. And instead of evaluating that force, what people often do is they evaluate the potential instead, because all you have to do is differentiate the potential to get the force. And it's that potential, 1 over r, that satisfies Poisson's equation. So that's the connection with all of that stuff, just to remind you. Okay, so now let's go on to parallelization. And so let's talk about the 2D problem, which is the first time it gets more challenging. So now, instead of being interested in the temperature in a one-dimensional object, I care about the temperature in a two-dimensional object. So I'm going to put down a 2D mesh on it. And at every mesh point, I want to write down the heat equation. And so again, it says the temperature with respect, the derivative with respect to time is still now the second derivative in the x direction and the y direction. So when I do all the math, I get 4 times my value, minus 1 times my nearest neighbors. That's the derivative in the x direction. But I also have to do it in the y direction. So I get 2 more minus 1's in each row. So to write down that matrix, there's going to be 1 row and column in this matrix for every point in this 2D mesh, so not counting the boundaries. And so I had to pick some order to order them. And what's the order? I just did it row-wise. So the first row is the first 3, the second row is the next 3 here, and then this row is the third 3. And so that means these 2 guys are my left and right neighbors, so they appear right next to the diagonal as they did before. But these appear 3 away because it's a 3 by 3 matrix. And if it were an n by n matrix, this minus 1 would be n away from the diagonal instead of 3 away from the diagonal. So it can have a very, very wide bandwidth. So now, let's talk about the design space of possible algorithms to solve this equation and what are their pros and cons. So to do this, I'm going to basically describe a common situation that happens when I have office hours and somebody wants to solve a system of linear equations. So they come into my office and they say, I need to solve a system of linear equations. I say, okay, use Gaussian elimination, dense LU. It works, there's standard packages for it. And it'll run on your serial computer in n cubed time. And they say, that's not fast enough. And then I say, well, tell me more about your problem. Well, the next thing they tell me is, well, actually, my matrix has a lot of zeros in it. This upper corner is all zeros. This upper corner is all zeros. In fact, if you go farther away than about this distance, I guarantee it to be 0. And they say, oh, you have a band matrix. In that case, there's a different variation in the algorithm. And if you tell me the bandwidth, I can tell you how much it costs. So we talk about that. And I say, oh, your complexity's gone down from n cubed to n squared. You should be happy now. You're asymptotically faster. And they say, well, it's still not fast enough. Then they say, okay, well, actually, I need to solve this problem over and over again. I'm not just solving it once. So what if I explicitly compute the inverse and then just do a matrix vector multiply? And I say, well, sorry about that, but your n by n matrix that's an inverse is going to be dense, and that's going to cost you n squared to multiply by your dense n by n matrix, so that doesn't make you go any faster. You tell me some more about your matrix. And then they say, well, I happen to know that it's symmetric. It's the same, top and bottom, A equals A transpose. And I happen to know that the eigenvalues are all positive. In fact, I happen to know the largest and the smallest. And there are only a few non-zeros in each row. There are only 5. And I say, oh, you want to use an algorithm called conjugate gradients. And then we talk about what the largest and smallest eigenvalues really are. And I say, oh, you've gotten it down to n to the 3 halves. You should be happy by now. And they say, it's still not fast enough. And I say, what problem are you really trying to solve? And they say, well, I'm just trying to solve the heat equation on a 2D mesh, right? And I say, oh, why didn't you tell me that? You should use either the fast Fourier transform or multigrid. That gets your complexity down to either n log n or n, and the lower bound is n. You're not going to go faster than that. So the whole point about this table is that I've given you all these algorithms, which are useful in different contexts, and they're sorted in 2 orders. From most general to the most specific, I make the most assumptions about the data, and also the slowest on the heat equation and the fastest on the heat equation. So we have actually online material where this is all arranged as a decision tree. So at every level of the tree, there's a question. And depending on whether the answer is yes or no, is your matrix banded or not, you may go left or right in the tree, and eventually at the bottom, it points you to all these different kinds of algorithms and software. But just so you know, there is no one best algorithm, but today I'm going to concentrate a little bit more, and we're going to have lectures later in the semester on how FFTs work and how multigrid work. Question, is there a microphone? If it's a short question, I'll repeat it, but maybe we should get a microphone in the meantime.
A short question.
Go ahead.
I'm sorry, it's kind of stupid. I'm just curious. I know FFT is good for solving the two polynomial and multiply them.
So the FFT is certainly good for multiplying polynomials. It's good for many different things that we'll talk about.
But it's it is actually performing a DFT, and how can you use the DFT to solve the maybe the heat transfer problem? So
the question is, how do we use the FFT to solve the Poisson equation or things like the Poisson equation? I will have a lecture on that later. It turns out there's an explicit solution for it, and it requires a 2-dimensional FFT if you're solving a 2D Poisson. We'll define what that is, or a 3-dimensional FFT to solve 3D Poisson. Then some scalar multiplications, and then an inverse FFT. So yeah, that comes later in the semester. And there's a microphone. It's on.
Okay. So you mentioned a 2D and 3D FFT. Does it mean the dimension of the vector input?
So a 2D FFT means the input is a matrix, and you do independent FFTs in all the rows, and then you do independent FFTs in all the columns. That's a 2-dimensional FFT. 3D is analogous. And there's lots of surprising, clever ways to make that go faster in parallel. Any other questions? Yeah, so this is advertising for later in the semester. It doesn't all fit in one lecture. Okay, and here's just a summary of the office hours. You can read that later. So let me just now give some very old data, some examples to say what metric of success should you use to pick an algorithm. And these are all different solvers applied to not quite the heat equation, but something very similar, a convection diffusion equation. And if you just go by your metric of success from homework 1, it would be speed, flops per second. In this case, megaflops per second. You can tell how old this data is. And of these 3 algorithms that were on that list of algorithms, Jacobi, Gauss-Seidel, and multigrid, Jacobi is the fastest, Gauss-Seidel is next, and multigrid is much, much slower. On the other hand, if you look at how long it actually takes to run, you have to know how many floating point operations they're doing. And as I said, multigrid is a linear algorithm, order n, whereas these are order n squared, and that's why it's 1,000 times fewer flops, and it takes 30 times less runtime. So depending on what your computer you're on, obviously this is what you care about, 7 seconds versus 2,000 seconds. But depending on your problem size and and other matters and how much the megaflop rate varies, it's not clear which one wins. Here, multigrid is clearly going to win. Okay. So let me just sort of summarize all these different approaches, and we're going to go into details in later lectures. You can either have explicit approaches, which means you're basically doing sparse matrix vector multiply, or implicit approaches, in which case you have to solve a sparse system of linear equations at every time step. And one way to do it is with direct solvers, so variations on Gaussian elimination or Cholesky, which take all that sparsity into account. And we'll have a detailed lecture on how those are parallelized later. And I should say there's lots of wonderful libraries that have been invented and you can just download. You don't have to build your own. And the other ones are iterative solvers, including like multigrid. If you look in the inner loops, what are they really doing? They are still doing sparse matrix vector multiplies, but maybe on approximations to your original matrix. So another thing that, just to repeat, sometimes I talk about sparse matrices, sometimes I talk about graphs. Mathematically, they're the same things, and I will go back and forth in that language as I talk about how to make things run in parallel. Okay. So now what I want to do is give you a few pictures about what kind of meshes come up in practice and why there are interesting challenges that come up. So far, I've just had these nice simple 1D, 2D, 3D meshes, but real meshes are much more complicated. But are there any questions about the material so far before I show you pictures of pretty meshes? Okay. So even though 1D, 2D, and 3D meshes are very simple, they're still useful building blocks for more general ones. And so one thing you can do is build complicated objects by putting together multiple meshes that are just connected to their boundaries. And then you can use the nice building blocks for regular meshes when you do more complicated ones. I'll show you some pictures there. The next more complicated thing is to have just general unstructured meshes. You have a finite element problem and you've had, somebody has broken it up into little triangles here and big triangles there, and you get what you get. And then you have to deal with that general sparse matrix, and I'll deal with some pictures there. And then the most interesting case are adaptive meshes, where you're going to have to change the mesh during runtime. So why would that happen? And I'll show you pictures. Suppose you have a flame front going through some material. You really need your high resolution right at the flame front, so that's where your small mesh is going to be, but that flame front's moving, so your mesh has to change over time. But let me show you the simplest case first, which are composite meshes. And so here's one we kind of made up. You could think of it as a bridge abutment, if you like. So each of these sub-rectangles is obviously a nice regular mesh. And so the way to think of this is that I have an unknown for every point in this graph, a row or column in my matrix. And whenever I have an edge connecting, say, vertex 1 and vertex 2, that means entry 1, 2 of my matrix is non-zero. So here's a nice regular part, and here's another regular part. And of course, what keeps the whole matrix from being, nice and simple is that it's connected at the, I have these connections between boundary points. So now, let me number everything and show you what the matrix looks like and what the meshing looks like. Okay, so what I've done here is I've taken this mesh, which is a nice simple 7x7 mesh, and it is the first, so 49 mesh points. And everybody is green, and so that corresponds to that green submatrix there, the first 49 entries. And since everybody is just connected to their nearest neighbors in a nice regular way, this green submatrix up here is a nice simple band matrix. It might not be, just look exactly like the Laplacian, but it's basically every row is the same where the non-zeros are, except right at the ends. And then here's the next entries, 50 through 91. That's that blue band submatrix. Then come these, that orange one, and so forth as we go down. So that would be nice and simple, but of course they're connected to one another. So let's see how the extra connections make sense. So for example, these green ones, the first 49, are connected to the next ones through those red edges, and that corresponds, is that visible? Yes, good. Corresponds to these entries here connecting green to blue. The blue is connected to its neighbors, to the green and to the red. So there's the green, there's the red. And here, the red, it has a more interesting connection because this one here is numbered last. And so if I look, then I see the red is connected to the blue and to the light blue, and it's also connected to the green, those little ones that are farther away. So I get all this kind of irregularity in there. And I have to take that into account when I try to solve this problem. Question?
Why no connections between the blue and the magenta?
Connections between blue and magenta here. Blue and magenta, those are these edges, these non-zeros right here. Those are connected, those correspond to those red edges right there. Yeah, it's a small plot. So all of this, I should say, this is a SPI plot in MATLAB, so you're welcome to take all of our MATLAB code and look at it yourself. So this is, what it looks like. So now, let me go ahead and run Gaussian elimination on this and just see what happens and see what kind of a graph problem it turns into. So here is that same picture I had before of my sparse matrix, and I've thrown away the colors. And now I'm going to run just plain old Gaussian elimination. In fact, it's called Cholesky on this matrix. And it's called Cholesky because since the matrix is symmetric, I only have to work on the lower triangle. And here is a picture of where all the non-zeros are when I run Cholesky on it. So whenever I had a non-zero here, I have a non-zero there, and it's colored black. But in addition to all of those entries, I get a bunch of new non-zeros because when I add one row of this matrix to another row, I may fill in a zero that wasn't zero before. Those are all colored red. So that creates more work to do later, and it also creates more memory that I have to take into account. And just to keep the numbers straight, the number of non-zeros has gone from about 4,000 to 11,000, and the total amount of work is about 300,000 flops. This is pretty small. So now, let me ask the question, how would I take that matrix and just reorder the rows and columns to make it go faster, to both create fewer red entries, fewer non-zeros, and to do less work? So it turns out that the right way to do this reordering, so these two matrices are identical, even though they don't look it. The only difference is I've reordered the rows and columns in the same way. And the algorithm is exactly the same algorithm that we talked about before for graph partitioning. That same trick, about which we'll have a lecture, gives you this. And now when I do Cholesky on this, I get many, many fewer red entries. I've gone down from 11,000 to 8,000. And the amount of work has gone down from 300,000 to 200,000. This is a really, really tiny problem. If I were to do this on a really large matrix, I get asymptotic improvements, really big improvements from doing this particular reordering. So this is yet a graph partitioning, and for which many, many good software packages exist. So that's all reasonably regular looking meshes. So here is another example, just so you know what an irregular mesh looks like. So this is a discretization just in 2D around an airfoil. If you want to do this yourself, just go into MATLAB and type load NASA airfoil. And it's all kind of built in for examples. And here, why is there a finer mesh? It's so fine you can't even see the mesh points around the border. It's because that's where you have the turbulence and the airflow. And so you need a finer mesh to resolve what's going on around there. And so here's what the sparse matrix looks like if you do a SPI plot. And so there's a lot of dust. Most of it's along the diagonal, but there's a lot of dust scattered around. And here's what happens when you do Cholesky on it and you get a lot of fill-in. And again, you can imagine figuring out how to do this ordering correctly is a challenge. So that's one source of irregularity. Here's another one. We want to build it ourselves. So here is a nice regular mesh on a 3D cylinder that's been created. And what we need to do to run some of our algorithms is come up with approximations of this which have fewer mesh points, so lower dimensional. So how do we do that? Well, the simplest thing you could do is take this approximation of my tube, throw away every other mesh point, so you get a coarser one, about a quarter as many, and then you still have to figure out who's connected to whom. And so if you throw away a point here that was connected to two other points, you reconnect those 2 points here, even if they weren't connected before. So in other words, if I have 3 points, throw away the one in the middle, then I connect the two on the ends. And you can do that in 2 dimensions and 3 dimensions, so I get this coarser approximation of my 3-dimensional tube, which I'll use as a starting guess to solve this one faster. I'm going to use the same idea recursively. I'm going to take this and get an even coarser approximation of it, which gets less and less regular looking. And I can do that one more step until I finally get this messy thing, which is still in some sense an approximation for that. So let me give you one more interesting example, which was done across the way in Echeverry. And here, the goal was to have better treatment of osteoporosis patients. So the medical question is, you have an old person who may have osteoporosis, they fall down, are they likely to break their bone? And if so, what sort of treatment should you give them? So the canonical way that people have done this in the past is you just do some bone density measurements. And if the density is too low, then you know how to treat them. But that is still pretty approximate, and there's a better way to do it. So this is a project that was with Professors Panos Papadopoulos and Tony Keaveney and a joint postdoc, Mark Adams, that we had. And so what they wanted to do was make this a finite element problem. They wanted to take a real bone, this is a real bone from a cadaver, and do a finite element analysis of it and ask, how hard would this patient with this bone, former patient with this bone, have to fall in order for it to break? And is that a likely scenario that this bone would break? So how do you do a finite element model here? So what you do is you take that vertebrae and you put it into a micro CT scanner, and you create a full 3-dimensional image of that at 22 micron resolution. So that's in a very, very low-level detailed model of that very relatively large bone. And so here's a picture of what that looks like. And so you can see its bone is mostly air, no surprise. And there's even more air when you have osteoporosis. And then what you do is you do a meshing. There's some software tools that will create a mesh on that. And in this case, one fine element was a 2.5 micron cube, 44 micron cube, and so and that was just applied to a little. It wasn't the whole vertebrae. It was just a 2.5 cubic millimeter subcube of it. That led to and here's what it looks like, just for that part of it, and that created a sparse matrix of dimension 537 million. Right, so that is the problem that they had to solve. And so what do? You write down, the equations of motion, and you ask, how much force would I have to exert on this particular piece of bone in order for it to break? And is that consistent with falling down 3 steps, 4 steps, different accident scenarios? And so then what they did was they came out with some predictions, and they took that original bone and they tested it in the laboratory, and they were very accurate as to how much force you had to exert on it in order to break it. And so this actually won a Gordon Bell Prize, which is sort of the top prize in parallel computing world, in 2004, for solving this problem. And so now what they went on to do was to use this to try to come up with a mechanism for actually treating real patients. Now, you can't take a bone out of a real patient and do this particular experiment, and you can't use this much radiation on a real patient, in vivo. So what they did is much lower resolution, analyses on living patients in order to get this to work. But if you do it, resolve it finely enough, then it does work. Okay, here's another example that was also a local problem, and this is where you have to change your mesh adaptively, and that would be done, as I mentioned before, if you have a moving front. In this case, the front is the front of a supernova. And so this is a supernova exploding, and it's a little hard to see, but you can see this two-dimensional slice through it's a three-dimensional mesh, and it's much finer near the boundary. And then as the front of the supernova moves out, it gets finer and finer. And here, minus the mesh, is what they're trying to resolve at the front. And so there's a lot of parallelism here, and what you need to do is, as these little subsquares, cubes move out, you have to assign them to processors in a dynamic way and try to exploit parallelism both between them and on top of them. There are a lot of projects that have tried to do this over time. Titanium was one that was done here a number of years ago. There's a package called Chombo, done by Phil Colella, who's a member of the National Academy at LBL. He has another colleague, John Bell, who has an analogous project, also in the National Academy. Scott Baden is up there. He built a tool like this called KELP at UCSD. So there's lots of different activities here and interesting parallelization issues. So what are the challenges for these kinds of meshes is how do you generate them in the first place? You may start with a physical description of the object. It could come from tomography. It could come from something higher level. So how do you generate a bunch of triangles? That's a challenge in itself. Well, we have an expert here on the faculty, Professor Jonathan Chuchuk, and he has some of the leading algorithms for doing that. Triangle in the two-dimensional case, and he has another tool in the three-dimensional case. Then the question is, how do you partition them so that you balance the load and minimize the surface to volume ratio? And as I mentioned, there's a lot of parallel graph partitioners we'll talk about. Parmetis is one of the best known ones. And then there are all the iterative solvers that run, Gauss-Seidel, Koleski, multigrid, and we will have lectures later about some of these widely used packages that you can just use. PETSI is one of them, and again, a Department of Energy activity. And then you may want to use a direct solver. That's sometimes the most efficient. And SuperLU is one that was developed here and is also widely used and is maintained at Lawrence Berkeley Lab. So to summarize, we've now talked about all the 7 dwarfs that I mentioned before, the 7 kernels that sort of build up all of scientific computing. We just talked about structured grids and unstructured grids as they come up in PDEs. And last time I talked about the need for FFTs, dense linear algebra, sparse linear algebra, particle methods, and then of course some things are embarrassingly parallel. And that fills in this entire column of the 7 dwarfs for high performance computing. And over the course of the semester, we'll also be talking about how do you parallelize graph algorithms and all these other things, but this is just for HPC. So, are there any questions? That's sort of the end of the sources of parallelism part. And we still have plenty of other things to talk about today, but this is a good time to stop and ask questions. So, in that case, we're going to go on to talk about homework.
Hi guys, so I'm going to give you a brief overview and motivation for homework 2. Give me 1 second. Cool. So in homework 2, you're going to be making a particle simulation or an in-body simulation, and then optimizing a serial implementation of it in the first part, and also developing parallel versions of the in-body simulation using 3 different parallel programming methodologies. But first, to kind of motivate why we're interested in particle simulations, I can review some of what you've talked about. So particle simulations basically work by putting a bunch of particles in a box and then studying how they interact with each other. So the particular, like a common one is Newtonian gravity. So you have particles that pull towards each other. Their acceleration is proportional to 1 over r squared, the distance. And these are commonly mechanics, biology, and astronomy. I thought it might be cool to kind of show you guys what one of these actually looks like. So we start out with all these particles randomly distributed. And then in this case, they pull towards each other. And so you can see fun things happening.
Black hole.
This simulation is a little bit inaccurate because the particles bounce off the side of the universe, which is not what actually happens. In that simulation, we started with the particles randomly distributed, but you can actually pick any starting positions that you want. So I made this one this morning for you guys. And we can see how those particles interact. Yeah.
Are you assigning random momenta for the particles at the very beginning?
Yes, I am in this particular simulation. So, yeah, so you can see there are different colors. The blue particles are moving really slowly. The red particles are moving more quickly. So you can see they all become red pretty quickly. But they do start out with a little bit of momentum. In our particular simulation, the particles don't attract towards each other, they actually repel one another. So this on the right is the simulation you're actually going to be working with. So the particles repel each other, but as you can see by the gray box, they only repel each other if they're within a certain minimum cutoff distance. And this is hard-coded in the assignment. So if you were to look at this problem naively, you first look at each individual particle, so you iterate through every particle, and then for each particle, you look at every other particle. So that's going to be an n-squared algorithm. However, since we have this cutoff distance, most particles are actually not interacting with each other. As you can see with that one particle there, there's only the green particle that's within the gray boundary. So you really only need to compare to a smaller number of particles that you could possibly be interacting with. And we'd like to avoid looking at these unnecessary pairs of particles. So the way to do that is pretty simple in this case. You can place these particles in bins, and then now you only have to check the neighboring bins. And since we keep the density constant as we increase the number of particles, for each particle, you're only looking at 9 for 9 bins times d, which is the number of particles that you have on average in each bucket. So for each particle, you do a constant number of operations. And now we have an algorithm that's linear in the number of particles. So the first part of your assignment is taking a naive n-squared problem and then using this binning logic to implement a linear solution.
Sequentially.
Sequentially, yes, that's the first part. So you have to assign these particles to bins. There are basically 2 different strategies you can use to do this. You could just delete all the old bins at every time step and then insert everything into a new bin. That could be expensive depending on how you implement your bins. And then the other option is that you actually maintain your bins for the entire simulation and then you move the particles in between the bins. And that could be tricky depending on how you implement it. Common issues that people encounter on this homework, in case you encounter them, are accelerating particles that just kind of move quickly across multiple bins. This is usually a result of interactions not happening when they should, because the particle is not interacting with particles that it would cause it to bounce in another direction. Another common occurrence is disappearing particles. And this is usually a result of the binning not working correctly. So a way to check that you're not experiencing this is to check the total particle count and make sure that it's the same throughout the simulation. Okay, so the first 2 parallel ones are OpenMP and MPI. You do OpenMP in the first assignment. And it's very similar to the serial setup. You split the particles into p equal-sized subsets, where p is the number of particles, and then iterate through this shared data structure.
P is the number of particles or processors?
Sorry, p is the number of processors. And then iterate through this shared data structure. For rebinning the particles or moving them in between the bins, you're going to have some kind of synchronization strategy, and that is either going to involve locks or atomics, depending on how you decide to implement your shared memory code. The second one is MPI, and this is somewhat similar to OpenMP, except you use messages instead of shared memory accesses. So the basic thing that you want to do is gather all the particles on the node, and then update the local particles. Before you start working on the parallel algorithm, you should work on the serial algorithm and make sure that you have it working correctly. You don't actually change the algorithm that much between the serial version and the parallel version. You just have to change how the work is distributed and how the data is distributed. So common issues for the OpenMP implementation are deadlocks. So if you actually use locks and you have threads competing for the same bins to insert or retrieve particles from them, you should try to be careful and make sure that you don't have threads accessing or grabbing multiple locks at the same time, because that can lead to deadlock. Or if you do choose to do that, think very carefully about what your strategy is going to be to avoid threads waiting for the same resource. Another common thing is race conditions. If you have shared particles and you're moving them in between bins, you can accidentally update a particle incorrectly. And so be sure to use synchronization when you're updating any shared data structures. Another thing is just slowdown compared to the serial version. So try to avoid excessive synchronization, but still make sure that your threads are working on the correct part of the program. And a good way to do this is just having a barrier after each parallel segment. With the MPI implementation, it's very similar, but you're going to use messages instead of shared variables. And so keep in mind, this does take longer to code correctly. That's why we give you 2 weeks for the MPI version. And if you use blocking send and receive pairs for sending your messages from processor to processor, keep in mind that you need to, usually you want to post the receive before you post the before you post the send, and that if you do this incorrectly, deadlock can occur. So you can also use non-blocking sends and receives. It makes the implementation somewhat similar, and you tend to get better performance. Common problems are particles not interacting with each other, or particles disappearing, just like the shared memory version, but now with messages. And yeah, that's all the introduction material I have for homework 2. Do you guys have any questions?
If you have questions later, please.
Yes, I think these are your next. Are these your next slides, or are these the old slides?
Those are the old ones.
Okay. Here are your new slides.
Yeah. Okay, I wanted to revisit a topic that is part of homework 1, which is how do you organize algorithms to minimize what's the most expensive thing that computers do, which is moving data, and show that the idea that you're doing on homework 1, which is tiling matrix multiply, actually works for arbitrary code that looks like loops access with arrays inside of the loops. So just to repeat, communication, that buzzword means moving data. It could either be between main memory and cache, or between different levels of cache. All of that's expensive, and we want to minimize how much time and energy we spend doing that. So what I'll do is very quickly recall matrix multiply in the blocked version, and what is the lower bound, and this time I will actually do a very brief, intuitive version of why that lower bound is true. And the reason for doing that is I want to say, how does that all extend to arbitrary code that looks like nested loops accessing arrays? So the same mathematical or geometric intuition that applies to matrix multiply applies to very, very general code. So here, just to remind you, is the optimal matrix multiply, not with every optimization, but with the tiling. So I have little n by little n matrices I want to multiply. I'm going to break them up into blocks of size b by b, and then I'm going to have 3 nested loops over the blocks. And what am I going to do? I'm going to, in the innermost loop, I'm going to do a b by b matrix multiply and update a b by b block. And so each of these little blue squares represents a b by b block. And so the question is, how do I choose B? And so let me assume that I can fit all 3 of these B by B blocks into cache at the same time. And in that case, I'm going to read 1 block in of C, and so that's going to cost me B squared reads. Then I'll read a block of A, a block of B, do all the work with no more memory traffic, and then write C out when I'm done. And so if I do all the counting, this 1 line, read a block, costs me B squared. How many times do I do it? Well, it's in 2 nested loops of size capital N, so it's capital N squared B squared, and that's just read the matrix once. Can't do any better than that. Here's where all the real communication is. How often do I execute this line of code? It's capital N times capital N times capital N, so capital N cubed times B squared, and that's little n cubed, the matrix dimension, cubed divided by B. And so if I add that all together, I get basically 2 little n cubed over b. How small can I make that? I can't make b bigger and bigger because I'm assuming that 3b squared is at most m. So how small can I make it? It's basically order n cubed divided by the square root of the cache size. And so what we claimed in an earlier lecture is that you can't do better than that. No matter how you reorganize that code, as long as you're doing, n-cube matrix multiply, you're not allowed to do Strawson or any of those clever algorithms. No matter what order you do those n-cubed operations in, you can't do any better than n cubed over m to the 1/2. And that was proven back in 1981 in a way that was just very special to matrix multiply. But then there was a much more general intuitive proof that came up later, which actually generalizes to the parallel case, which I'll tell you, and basically way beyond matrix multiply. So let me give you a hint of how that works. So the way I'm going to think of my code, so imagine you're executing your code, on your serial machine. What is it doing? It's doing a sequence of operations. The only ones I care about are the adds, the loads from slow to fast memory, the multiplies, and the stores, where I move data from fast memory to slow memory. Whenever I do an add or a multiply, that's all lives in cache, no memory traffic. And every load or store, that's where the expense is. That's where I'm moving data one way or the other. And so what I want to do is to count the number of loads and stores that I have to do, given that I'm doing the usual 2n cubed matrix multiply, and that I can only fit capital M words into my cache. So here is the 4-step outline of the proof. Think of this instruction stream, basically, lots and lots of multiplies and adds and loads and stores. I'm going to break them into segments. I'm going to analyze each segment separately. And each segment basically consists of m loads and stores. So I just start going down through the instruction stream, counting loads and stores, and as soon as I hit m, that's the first segment. Then I start counting them again. When I get to m, that's the second segment, and so forth. Now, the magic occurs. Somehow, I'm going to bound how much work I can do if I only have done m loads and stores. So that's going to give me a bound on how much data I have available. That's going to tell me how much useful work I can do, and I'll tell you where that comes from. But let me just call it capital F. How many flops can I do with a limited amount of data? So if I know that I can only do F flops per segment, how can I do all the work in the program? Well, the total work in the program is the number of segments times the flops per segment, and that better be 2n cubed, right? Because I need to get that much work done. And so the number of segments is at least the total number of flops divided by the number of flops per segment. So if I know how many segments I have to have, what's a segment? It's defined by doing m loads and stores. So the number of loads and stores is m times the number of segments. So this is going to be my lower bound. I know m, I know that, it's 2n cubed. What I don't know yet is a bound, an upper bound, and how much useful work I can do with just that much m words available. And for those of you who really want to be rigorous, I should have actually not used t divided by f, but rounded down to the nearest integer. But it's the same idea. Okay, so what I'm going to do now to get this upper bound on F is I need a geometric model of the work that's going to be done. So here's the idea. I have 3 nested loops, so n by n by n. I'm going to model that as a cube, as an n by n by n cube to represent the work done by the algorithm. So here I'm doing a 3 by 3 matrix multiply. And so each face of the cube is going to represent one of the matrices. So that little square, 1 by 1 square, that's going to represent A11. That'll represent A12. That's the B face. Each square represents an entry of B. And up there is the C face. So now, what about the little cubes inside of it? The cubes represent one loop iteration. So what does this cube represent? Well, this represents, please multiply A13 times B31 and update C11. So every 1 by 1 by 1 cube in this n by n by n cube represents one loop iteration. So the question that I have is this. So that cube represents that. So I have n cubed cubes, and there's all the work. So here's the idea. If I want to perform that particular cube of work, I need its 3 faces. I need that datum, and that datum. So if I want to do a whole bunch of different cubes worth of work, I need all their faces, right? That's the data that I need. And so here's the idea. Suppose that I have a limited amount of data, 1 segment's worth of data. It turns out I can only fit 2 M words. I can have M words in my cache when I start, and I can read M more words, during the course of the segment. So I can have at most 2 M entries of A. That's all that I have. 2 M entries of B and 2 M entries of C. So suppose I can only have that many squares on each face. How many cubes can they cover? That's the geometry problem. So let me tell you, sort of to give you the intuition, here's the simplest case. So here's that n by n by n cube, and suppose I wanted to do all of the work that's represented by that little brick in the center. So that's a little brick, and suppose it's an x by y by z brick, and so its volume is how much work I can do, the number of cubes in there. So it's x times y times z. And so what I want to know is, how much work can I do? How big can x times y times z be if I know the areas, the faces, if I know how many entries of A, B, and C I have? Well, what's the area of that face? Well, it's just z times x. What's the area of that face? Y times z. And what's the area of that face? X times y. So I know those 3 numbers. How do I bound that? Well, it's pretty obvious. I just multiply them and take the square root. And so the volume of this cube is precisely the square root of the products of the areas. So what's amazing is that this is true for arbitrary shapes, almost. So it turns out I can take an arbitrary set of cubes, so some arbitrary thing, and I can take its 3 projections or shadows. What entries of B, A, and C do I need? And there's this theorem that goes from mathematics, that goes back to 1949, says the number of cubes in here is bounded by the area of that face times the area of that face times the area of that face, take the square root. And that's an upper bound. Here, it's equality, but it's a bound no matter what shape that is. And that's going to be where I get my bound on how much work I can do, because I know I can have at most 2m squares there, 2m squares there, and 2m squares there. Okay, so here's the last slide of the proof. So I think I have 1 segment. I can have at most 2 M entries of A, B, and C, because I can start with M entries sitting in the cache when the segment starts, and I can read at most M more. And so how much useful work can I do? It's 2M times 2M times 2M, take the square root, and so that's 2M to the 3 halves. That's my bound on how much work I can do. So all I have to do is stick that in the denominator, and the number of loads and stores is bounded by M times the number of flops divided by that, and I get n cubed divided by the square root of m. And so that's where it all comes from. So it turns out that this is all I need to do to get a lower bound for the parallel case as well. Now that's odd. Let me try that again. All right, I don't know why it looks like that. Okay, so here's the parallel case. It's exactly the same idea, except now what I want to know is how much data has to move in and out of one processor, right? That's the most expensive thing, number of messages sent, for example, in MPI. So the idea is, think of the memory on one processor as the cache of size capital M, the fast memory. And think of the slow memory as everybody else's memory. It's the same idea. I want to know how much data moves between my memory, the fast memory, and everybody else's. So I'm going to use exactly the same formula. All I need to know is how much work do I do, and what's my memory size. Okay? So how much work do I do? Well, if I have P processors and everybody's, and it's load balanced, I'm going to do 1 piece of the work. So the numerator is going to change from 2n cubed to 2n cubed over P. And how much memory do I have? Well, that's an interesting question, but the most obvious thing to do is say everybody gets an equal share of the data, right? So instead of having 3n squared, I have 3n squared over P, right? Because all the matrix has to be spread out over everybody's data. So I'm just going to say everybody gets 1 piece of it, 3n squared over P. And so what's my formula? It's the same one. My fast memory size, that number there, times how many flops I have to do, divided by this, which is the same formula as I had before, and lots of things cancel, and I get n squared divided by the square root of the number of processors. And it turns out there is an algorithm that attains that, and we will talk about that in a future lecture. But that's going to be our goal for an optimal matrix multiply. Now, okay, I'm doing fine. So now I claim that this picture for matrix multiply generates arbitrary code. And so to give you a hint without doing all the math, I'm just going to give you some intuition of how to generalize it. So here was our naive matrix multiply. Here was our block code, just to review again. And here is the new general theorem that applied to this. And it says that if I pick the block size to be m to the 1/2, the number of words moved is the number of loop iterations divided by m to the 1/2. So because that's the block size, remember, I'm doing it m to the 1/2. So where do all these 1/2s come from? Right, that seems, so I want to have a general approach that will give me different numbers than 1/2 for different code. So let me give you sort of some intuition of where that 1/2 would come from. I'm going to do it by writing down a sort of a very simple natural linear program where I don't know that it's 1/2, but when I solve the linear program, the answer will be 1/2. Okay, so I'm going to assume that I'm going to write down my tiled code. So I'm going to have 3 nested loops, which break it up into tiles. And I just don't know the tile size. I want to write down an optimization problem for the tile size. So I'm going to let m, the cache size, to this unknown exponent be the tile size for loop I, m to the xj be the tile size for loop j, and so forth. And so here are my 3 innermost loops. I'm going to do an m to the xi by m to the xj by m to the xk matrix multiply. And the question is, how do I pick those exponents? Those are going to tell me the block sizes. So here's the optimization problem. I want to maximize the amount of work that I do. And I have 3 nested loops, so I just multiply the loop bounds. I want to maximize the amount of work that I do. But I have a constraint, and the constraint is that all the blocks fit in cache. So how big is, for example, C? C is the I by j matrix, so it's going to be m to the xi by m to the xj. And so my constraint is that this is how big the C block is, that better fit in cache. And I have 3 of those constraints. So that's not quite a linear program, but it almost is. All I'm going to do is take the exponents, right? So what I want to do is I want to maximize that exponent subject to all the constraints. xi plus xj is less than or equal to 1, xi plus xk is less than or equal to 1, and so forth. That's this very, very simple 3x3 linear program, and the answer is 1/2, 1/2, 1/2. And the sum, I'm going to give it this name, S sub HBL. HBL are the initials of 3 famous mathematicians, whose work this relies on, and I'll tell you who they are in a future slide. And then the theorem says that this is optimal no matter how you reorganize matrix multiply. And the number of words moved is going to be m to that magic exponent S sub HBL minus 1. So that's what the general theorem says applied in this case. But the linear program is a perfectly natural linear program to write down. So how does this generalize? Again, for matrix multiply, all I needed to know is that I'm iterating over the cube, some subset of triples of integers. That's really all I needed to know. And I need to know what the subscripts were. That I had, that one array had subscripts I and j, another subscript or matrix had subscripts I and k, and so forth. So this is how it's going to generalize to arbitrary code. I could write down arbitrary number of loops. They could have any loop indices you want. I could have as many lines of code as you want. I can have any subscripts that you like as long as they're linear combinations. So you can write down an arbitrary mess. All I need to know about that mess is that how many subscripts do I have? In this case, I have a k-nested loop, so I'm iterating over some k tuples of integers, and I need to pull out the subscripts. So in this case, C has a subscript, which is that linear combination. I just make a list of them. That's all I need to know. And my goal, which we've attained recently, is I want communication lower bounds in an optimal algorithm for any program that looks like this. Okay, so let me just sort of sketch what the answer is without doing any proofs. So given any program that looked like that, then there's this magical exponent, S sub 3 famous mathematicians, such that the number of words moved, no matter how you organize that code, is lower bounded by the number of loop iterations, n cubed for matrix multiply, divided by the fast memory size to that magical exponent. And where does that magical exponent come from? It comes from solving a linear program. I showed you what the linear program was for matrix multiply. Now there's a lot more math needed. It uses group theory and functional analysis, and I won't go into it. You have to write down a bunch of inequalities over all subgroups of k tuples of integers. So I'm happy to give you papers if you want to read about it. And the proof depends on a recent result in pure mathematics by my colleague Mike Christ in the math department, Terry Tao at UCLA, and a bunch of other people. And it's a generalization of something called the Holder-Braskamp leap inequality. That's where HBL comes from, which was originally continuous to abelian groups. And this is sort of the ultimate inequality. It has as a special case Cauchy-Schwarz, Loomis-Whitney. Every inequality in math you've heard about is a special case of this one. So that's why it generalizes. So that's the lower bound. And so the next question is it attainable? But first, can I even write it down? Because if I look at this, I have an inequality for all subgroups of k tuples of integers. That sounds like an infinite number of inequalities. But the good news is that all of these coefficients are just integers between 1 and the number of loop indices. It really is a finite number it really is a linear program. But I still have to write it down. So when we first started working on this, we tried to ask ourselves, is there an algorithm for writing it down? It turned out to be equivalent to a well-known open problem that nobody's figured out for 40 years, Hilbert's 10th problem over the rationals. So that was sort of an issue. But then we realized we didn't have to write down every inequality. We could just write down a subset of them and get the same answer, get the magic exponent. And it's decidable, and we have an algorithm for it. And there's a lot of special cases that come up in practice where there's a nice, finite way to write down what it all is. So that's under control. So the next thing that we did was, can we find an optimal tiling, right? And because if you write down the original nested loops, you may not be able to tile them the way they're written down. You may have to have some other weird tile. The shape may not be a brick. And it turns out that you can always construct an optimal tiling, no matter what the code looks like. And there's some assumptions there. We don't get all the constants right all the time. I'm just being honest. So it's a big O result. And it depends on the loop dependencies. So matrix multiply, I can do all those inner loops in any order that I like, because I'm just adding stuff up. So I can reorder it and get the same answer. If I have another kind of algorithm, if I do everything in a different order, I may not get the right answer. So let me just assume I'm allowed to do the reordering. And I have to assume that my tile shape fits inside the loop bounds. So here's an example, matrix vector multiply. That's, if you like, a special case of matrix multiply, except one of the matrices is really skinny. And you can't hit the lower bound because that I have here, because you can't do better than read the matrix once. You have to read in every entry once. It doesn't get better as the cache gets bigger. And so that's because the tile size is this square that doesn't fit in the vector. So, and it comes from doing a linear program. So I'm just going to show you some pictures, some eye candy, to show you what these optimal tiles look like. And I'll do it for a very simple case, just 2 nested loops, where I'm doing the n-body problem. So I'm going to take all pairs of particles and maybe compute the potential between them. So I want to take all the particles A0 through AN, B0 through BN, combine all pairs, and I want to optimally tile that. So let's suppose, to keep the picture, so here's all the i's, here's all the j's, and each dot represents a loop iteration. So what's my optimal way of organizing this code? So what's your intuition? Suppose I read in 5 entries of A and 5 entries of B. How much work could I do? 5 times 5. I could take all pairs. So to keep the picture simple, let me suppose my cache is of size 10. Then I'll read 5 entries of A, 5 entries of B, and I can do all of those 25 loop iterations. And that's an optimal tile, because I can keep going, and eventually do every point, in that space, in an optimal way. So now, your intuition is perfectly good for that. So let me just change it a little bit. I'm going to change that subscript from J to I plus J. And I want to do just as well. I want to read in 5 entries of A, 5 entries of B, and still do 25 pieces of work. So now, what does the optimal tile look like? It looks like that. I'm going to call it slanted. So I'll read in those entries, and now those are the ones that I can do. And the good news is that still tiles the plane. You can still do it. So now let me go to the most general case, which may not be practical. Let me have an arbitrary linear combination subscript for A, an arbitrary linear combination subscript for B. I still want to read 5 entries of A, 5 entries of B, and do 25 pieces of work. What do you think the optimal tile looks like? There it is. So it's still sort of a parallelogram, but it's not contiguous anymore. But I can still do 25 words, and it tiles too. I can do that one next, and that one next, and that one next. But does anybody see a problem? I've missed a lot of the little black dots, right? I actually haven't done everything. But the theory goes on to say, no problem. All I have to do is take all of these tiles and shift them up by 1. I'll do another independent set of work. Shift it up by 1 again, 1 again, 1 again. 5 copies, and I've done everything. And so that is the optimal tiling, and all of this comes out of some group theory that analyzes these subscripts. And so anyway, that's all I'm going to say about that, and there's plenty of papers to read about it if you want more than eye candy. So I'll stop there.